lesson 18. Then we'll do lesson 19 after that, and then we're done for everything that's going to be on the second exam. Okay, this is 5.5 from the textbook. We are finding equations of linear models. So don't write this down because I'm just going to recap where this is all coming from, because this is compiling or putting together things that we've already learned. In lesson 13, sorry, my bad, 12. 12, we had some data, and then we did some linear models off that data, and I did mention that if we had face-to-face classes, you would have plotted those points on your own. You would have sketched the line that you felt best fit that set of data, the line that's closest to the points, and then you would make estimates off of your line, which might be different from the way I drew my line. Because I can't rely on everybody having graphing paper and printers, I just did the line for you, so we're taking a little bit of a shortcut, and then you would make estimates off of that. Again, don't write this down, I'm just summarizing things you've already done. In lesson 13, 14, and 15, you learn equations of lines, and most of them were like y is equal to 3x plus 2, where you would just be able to count 1, 2, 3 up, 1 over, things like that. But we did learn how to take 2 points. Sorry, yeah, we did learn how to take 2 points. In lesson 15 specifically, you would take your x1, y1, x2, y2 points, and you would first find your slope. I'm going to erase this immediately because I'm just, again, recapping, trying to make sure we understand that we're going to be using all these things. We're going to be talking about linear models and making estimates off of it. And we're also going to be putting together equations of line using that, but they're not going to be as nice. We're going to have to do some rounding, which is why we did a whole lesson on rounding before we got to this. Okay, so I'm just going to trace an example. The value of a car decreases linearly, I mean it's going to in the form of a line, from $6.2 thousand in the year 1983 to $2.4 thousand in the year 1991. Okay, so we have the value in 2 points in time. So essentially we have 2 points, and it decreases linearly. So we're just going to see the graph, the value go down. I'm going to graph it in a little bit, so don't worry. But just give you a preview. And then they're going to define some variables. Let V be the value in thousands of dollars and T the years since, and the reference year is 1980. Okay, so we had problems like that where we had a scatter plot and a linear graph, and then I use those variables and the concept of a reference year. So that's all things we've done before. So I can't spend time talking about it too much again. But yeah, okay. And let's start. Well, actually, this is not even a question yet. Our first question is to find the equation of the linear model to describe the data. I'm going to write that in a little bit. The instructions here does not say to graph it, but I'm going to graph it anyway to talk about it. So let me just graph it and give you a visual idea of what this looks like. So this is very similar to what we did in homework 12. We have T, the year since 1980. V, the value here. I'll scale it for you. I'm going to go by 5s along the T. Okay, and T is again the number of years since 1980, so 1980 is there at 0, 1985, 1990, 1995, and you can go further if you needed to, but we won't. Values they're in thousands of dollars, so rather than putting like 2,000 or 3,000, I'm just going to put 2 and 3, and they represent thousands of dollars. Again, we did this in homework 12. I'm going to go by 2s, 2, 4, 6, 8, 10. And some of my graphs that I had in that homework, I put little tick marks in between, even though they weren't labeled, but that was just to get a better idea of where 1 and 5 are. Just a halfway marks between them. Okay. Now, what we're trying to do here is we're trying to grapple with this idea that the value in 1983 was $6,200. So I'm going to try and graph that. 1983, I need a t-value, that'd be t is equal to 3, so about here. And then 6,200 is about there, so I'm going to put a point there. And then 1991, you got to remember it's not 1, it's since 1980, so it's t is equal to 11. And then I got to go to 2.4. And if it's starting to get confusing, I agree, which is why I'm going to recommend highly that before we even get started graphing or doing the thing that we're going to do, finding the equation of the linear model, let me summarize the points that are involved, which I got to put somewhere, and I guess I can, I'm going to put them right here. No, I'm going to put them over here. Okay. So I'm going to write the information that I have in this paragraph, and I'm going to pick it out and put it in the form of ordered pairs, which is what I'm going to be working with. So rather than doing what I was doing, where I was like, oh, 1983, and then losing track of things and getting confused, let me just sort it out in clean coordinate format. Now we don't have x and y here, we have t and v. And keep in mind which one is replacing x and which is replacing y. Sometimes I refer to t as the independent variable, which means it's like x. So that's going to be a t-value, that's going to be a t-value. They're going to say the value is a dependent variable. You got to remember that means it's like y. So instead of y, we're going to have a v value and a v value. Okay, and now you have to use the numbers, the information given here, as defined by the variables. We're converting the year to the t-value, the number which is 1980, and the value is in thousands of dollars. We're just going to use as is as a value. So what's my first ordered pair? It's based on the year 1983 and the value of 6.2. I got to convert that to a t-value. That's t is equal to 3. Everybody know that, right? It's 1983 is my year. My t-value is the year since 1980, so I subtract that, and I get my t-value for that corresponding year of 1983. It's t3, comma, 6.2. Okay, I mentioned that I was trying to do 3, but I'm going to pick it out and write it as ordered pairs first. Go ahead and give me go ahead and figure out, think about what the other point is based on this value of 2.4 thousand in 1991. Think about it, make sure you don't use 1, using the reference year 1980. So you're doing 1991 minus 1980, and that gives you, that's your t-value, the difference in years, how many years it's been. And that gives you 11. It's 11 for 1991, and the value is 2.4 thousand, but we're using the number of thousands, so we're using 2.4. Those are the ordered pairs for that data, those 2 data points, the value at 2 different years. And now it's going to be easier for me to graph them just using ordered pairs. 3, comma, 6.2. That's what I was trying to do earlier. It's a lot easier when I can just see ordered pairs rather than having to pick things out in the paragraph and switching the years and the numbers and mixing them up. 11, 2.4, right there. And now, in theory, the value could go up and down and all over the place, but they're specifically saying it's decreasing steadily in a linear fashion. They didn't use that word, but that's what it means, decreasing linearly. It just means a line. And later on, in lesson 30-something, way like a month from now, we are going to have to read carefully because there's going to be a different type of decrease or increase called exponential, and we'll have to make that distinction between the two. But for now, we're not getting to that. It's always, for this homework at least, and this exam, it's going to be linear. This whole lesson is, this whole exam is about linear equations and lines. So I want to just draw a straight line through it. I want to kind of make it accurate. Oh, this is not accurate at all. Okay. Be aware, I'm telling you right now that's not accurate at all. It's a hand-drawn graph, and it's by no means is it going to give me accurate predictions. But That's not even what I was supposed to be doing. I haven't even asked the question yet. That was me just making sure we know visually what's happening with the value of this car. Your actual first question. Is to find the equation of the linear model to describe the data. And it's not going to come, it's going to be an equation of a line, but they're not going to be nice whole numbers or nice 2/3s, rise or run. It's going to be weird decimals. So I'll need to specify, and if I don't, round wherever you want. 2 places will be pretty standard. We're going to round figures to 2 places, 2 decimal places. And again, that's why we did a whole lesson on rounding prior to getting to this lesson. Okay, we're going to do this. I need more space than that. I can erase this and this. Keep in mind that all the information that I need here I did pick out and they're in that form. Okay, and so as I do this, I'm going to work with those coordinates. But if you need to come back to this, you can rewind the video. Okay. So let me summarize what we're doing. I'm continuing part A up here. Probably do more detail than I need to. First of all, what you would need to do is make sure you have your ordered pairs, because we're going to treat it like finding the equation between 2 points, which you did in lesson 15, I think. Okay, anyway, you would do the same thing that I did over there. You would figure out 1983 is year 3, the value is 6.2, 1991 is 11, your value is 2.4, and even though I specified we have to know their t and v's, for the purposes of working out an equation, we can temporarily imagine them being like x and y, because we're going to go through the process where we find the equation of a line between 2 points. So I'm going to temporarily pretend 3 and 6.2 are x1, y1, 11, 2.4 are x2, y2, because what I need to do is do the whole process of finding the equation of a line. And I'm not going to go through the steps in detail because we've done it before. You first use the 2 points to find the slope. 2.4 minus 6.2, y2 minus y1 up top, over 11 minus 3 in the bottom. And it's not so nice, and I definitely can't do this in my head. I mean, I could, maybe. But I wouldn't rely on it for sure. 2.4 minus 6.2. I'll just do the top and the bottom separately. 11 minus 3 is 8, so I'm just going to divide this by 8. I got negative 0.475. It does say to round figures, and that's a figure. We're going to round to 2 decimal places. If you don't round it and use all those 3 digits, negative 0.475, your answers comes out slightly different to mine, but I don't think it's going to be a big deal. I won't mark you off for it. But if you do want to follow instructions and get the exact answers that are on the back of the homework, you're going to round your figure to 2 decimal places. So we're going to round it there at that 7. And so it's going to round up because of that 5. And so I'm going to use a slope of negative 0.48. I'm going to circle that, but that's not my answer. That's the slope, but that is one of the crucial pieces there. And so that's the slope of the line. Why is it negative? Because it's a downward sloping line. So we're getting the equation of that line that I drew there. And it definitely has a downward slope. Next step in the process of finding the equation of a line. Y minus y1 is equal to m times x minus x1. Point slope form is what I'm always going to be using for that. Even though there is another method, and you can use it here, but you got to make sure you can do that if you're going to go that route. All right. In this situation, we discussed it. I can use either point. And I've said before that if you use either point in homework 15, you get the exact same answer at the end. Now, I have to prep you. If I use that point, I'm going to get one answer. And if I use that point, I might get a slightly different answer. They might not be exactly the same. They'll be very close. You should only be off by like a 0.01. And it's because we're doing rounding. So the figures that we start working with are not going to be 100% accurate. They're rounded figures. And that means that 2 equations using that or that could be slightly off from each other. But it should be very, very close. So be conscious of that. I'm just going to use the first one by default. So y minus 6.2 is equal to, my slope is here, negative 0.48 times x minus 3. Okay, and I'll work it out. That's why I had to do a couple of these with decimals. When you were learning how to do this, I threw in a couple on the homework that were decimals just to get you used to the idea that you will eventually have to do this using a calculator. Watch the signs on your own. That's a negative, distribute times that negative 3 would be a positive whatever. I don't know what that whatever is yet. 0.48 times 3 is 1.44. Again, negative times negative will make it positive. So I would make sure you are conscious and keeping the signs positive or negative in mind on your own. Don't rely on your calculator to do it. Next step, I'm going to add 6.2 to both sides. And I got to do it on my calculator. And I'm doing this one a little bit slower, but I'm going to speed it up as I go, as the next example. Not as many steps. Okay, so my equation of that line is y, well, it's actually not this, but I'll talk about it in a little bit. Y is equal to negative 0.48x plus 7.64. That's the equation of the line. Let me double check it. Yeah. That's the equation of the line through these points, x1, y1, x2, y2. Now, you don't get full credit for this because it's technically wrong. Our original problem, and even the graph shows it, does not have an x and y variable. It has a t and a v. I only used x and y because I'm used to these formulas being in x and y, but at the end, I need to convert it to an equation with value v in thousands of dollars and t the number of years since 1980, and therefore all I need to do, it's a minor thing, but I need to replace y with the y variable up there. V, value in thousands of dollars, is equal to negative 0.48. The slope and the intercept are still valid, it's just my variables are not x and y. Instead of x, I have t, the number of years since 1980, plus 7.64. And that's my model for v and t, the value of this car in thousands of dollars, t, the number of years since 1980. That's the equation of this line right here, with again, a t and a v axes and variables, not x and y. So you work with x and y to do your computations because you're more familiar with that. Make sure you switch it at the end to the actual variables used in the problem. Okay, that's part A. We're done. I'm going to pause it here. I'm going to have a lot of follow-up questions. We're not going to use that model to make predictions and talk about it, but I like to chop up my videos so I don't have to do the whole thing if I mess up. Okay, part B. Use the equation of your model. Now, at this point, you have two representations of the model, the linear model for this data. You have this hand-drawn half-assed graph, which is not accurate, and you have the equation. Now, for any predictions you're going to be making, the equation is going to be far more accurate than my hand-drawn graph. But they should be roughly the same. Using that is very similar to, or it's analogous to you making those estimates off the graph. It's just that these are going to be more accurate. They're down to the hundredth, so they're super accurate. And any problem I ask in this homework will specify that I want you to use the graph to make an estimate, or to use the equation to make an estimate. So be conscious, and I'm specifying here using the equation. We're going to use that. Use the equation of your model to, to estimate the value of the car, but I'm not going to write that, in 1986. Round to the nearest $100. And I'll talk about that rounding thing because it's a weird way to word it, but we'll figure out where that hundredth place is. But for now, don't worry about that. Don't worry about the rounding. Worry about using the equation of your model to estimate the value in 1986. I'm just going to copy down the model first. This is what we're going to be working with, the equation of our model right there. And basically to estimate the value, we're looking for V. And to be able to do that, you need the other variable. You need to be to do any kind of thing with this, you need to be plugging in one variable and solving for the other. So you have to know what you're plugging in and what you're solving for. They want the value, so they're going to be looking for V, which means they should be giving you something to plug in for T, which is a year. Now you don't plug in 1986 in for T. You have to remember how T is defined. I erased it already, but recall, T is a number of years since 1980. I need to convert this year to a T value. I'm always working with T values when I'm talking about equations and the graph and the intercepts and things like that. T is equal to 6, and therefore I'm going to plug in 6 in for T. So T, and I'm plugging in 6. And then you solve for V. Sometimes you got to solve something. You got to add. You got to do the solving process. But here the V's by itself already, and our answer is just whatever we get when we simplify the right-hand side. Watch out, negative. Don't lose that. It's negative 0.4. Oh, and I got to specify. I think I've done it before, but you have a minus button and a negative button. The negative button's next to on the bottom row, right next to the decimal point there. Right to the right of it is a minus sign, a negative sign in parentheses. That's for a negative number. The subtraction symbol here, it's got division, multiplication, subtraction. That's for subtracting two numbers, and we're not doing that. When I'm putting this negative here, I'm not subtracting from anything, so that's not subtraction. That's a negative, so I have to make sure I use negative 0.48 times 6. I can just do it in one shot, plus 7.64. And you need to follow order of operations, but the calculator knows that as well. So it'll multiply first, then add the 7.64 after. 4.76. And my units are, V was in thousands of dollars. This is not rounding as the instructions said, so let me talk about that. They want to round to the nearest $100. You have to know which of these digits is the hundredths place. You can go through that process of writing the full number out in standard notation if you want, but if you know which one is the hundredths digit, you can just round there, but I'm going to talk about it. So you'd have to imagine or even write out, here's my thousands place, and this is 4 whole thousands, that whole process of doing standard notation. The 7/6 spillover, I would aim the 0 there. So that value represents $4,760. And I haven't rounded it, as the instruction said yet, to the nearest 100. That's your hundredths place. I'm going to underline that. We're going to round it up because of that 6. So it's going to be 8. 4,800 is rounded to the nearest $100. And you can give that as your answer. That's perfectly fine. Or you can note that if you figure out where the hundredths place is going to be, that 7 is going to be the hundredths place. You can just round there. The same way, it's going to be 4.8. So you can give your answer as $4.8 thousand. And feel free to abbreviate. Thou is fine. I know what you mean by that. So either one of those is good. The rounding to $100 just means you have to be able to identify that 7 as the hundredths place if it were written in standard notation, even if you don't bother to do that. But either way is good. $4.8 thousand is the answer, rounded to the nearest $100. Okay, now that's it. We use the equation and we got a fairly accurate answer based on the computations. If we were to use a graph of it, so if you had a follow-up question that said use a graph of your model, right here, to estimate the value in 1986, you would still need to identify what t value we're talking about. T is equal to 6. You would do what you did in homework 12. Estimate where 6 is. Go up to your model. Go over. And I would have guessed 5.2 thousand because it looks like it's above 5 on my hand-drawn graph. Not accurate, but it would be close enough. And then I might ask you, is it close to the value you got from your equation? Pretty close, like 4.8 is right there. 5.2, my estimate's there. 4.8 is more accurate, but clearly it's just my hand-drawn graph is not, it's very small and not accurate. As long as you don't get something weird like 4.8 and 8.9, like it can't be that far off. But the difference between 5.2 and 4.8 is close enough. So you can see that. But anyway, this is getting the more accurate answer of trying to do the exact thing. Plugging in 6 into the equation and getting your V value out of it. Okay, we got more to do. I need the equation, but I have it there, so this is important. We're going to use this the whole way through. At least for this example, rather. my points are done. So let me just copy that model down. I have it there, but I'll put it up here for easy reference. You have it on your page in your notes, presumably, but I need it somewhere for easy access. Okay, ready for part C? Use the equation of your model. So once again, we're going to be plugging stuff into our equation. To estimate the year in which the card's value will decline to $4,000. Okay, so we're using the equation of the model. If we were doing it on the graph, which we're not, but if we were using the graph of our models to do this, we would go to 4 for $4,000. We would go over to the line. You've done this in homework 12. You would estimate, what do you think that is? I would say that's 8-ish. And then you would convert it to a year, and then I would say 1988 off of that graph. Well, but we're not using the graph, we're using the equation. So let's do this. Let me copy that down because we're using this equation. We want to find the year, and the year is related to that t. So to find that t, we need to be plugging in a value for the other variable. We need a value. And they give it to us right there. Make sure you don't put 4,000 here. Again, you have to remember how v is defined. You have to remember how t is defined. But what's relevant here is v is in thousands of dollars. It's how many thousands of dollars of value you have. You have $4,000 of value. So what's going in place of v is 4. For the same reason you look for 4 on there, you don't go all the way up to 4,000 because this is in thousands of dollars. So keep that in mind. It's deliberately written this way to make sure you're conscious of that fact and don't literally put, if you do not put 4,000 there, it'll mess you up and give you a completely way off answer. You need to know to use 4. Alright, from there, it's 4 for value. T is unknown, but once you plug it in, we'll be able to solve for t. I'm going to subtract 7.64 from both sides. Get negative 3.64. Don't worry about the negative, it's going to cancel out when I divide by negative 0.48. Okay. It's a negative divided by a negative now, so they're going to cancel and give me a positive. So when I type it into my calculator, I'm not going to bother with the negatives. I'm just putting 3.64 divided by 0.48. I get 7.58. Now, just as before, we need to make sure we give the answer as they asked for it, and they asked for a year. This is a t value, so we have to convert the t value to a year. And since they didn't specify right around, but they asked for a year, and just based on our convention of giving years as whole number of years, again, we don't say 2020.7 or anything like that. So we're going to round this to a whole number t value, and then convert it to a whole number a year. So for years, you need to know that automatically rounding to a whole number. Just to the closest, it's going to round up to 8. And then when I convert it to a year, that's 8 years since 1980. Here I would add it back to the reference year and get 1988. That is actually exactly what I estimated when I did it off the graph, but again, the graph is not as reliable as this. The closest year is 1988. That's it. If you're really thinking about this year concept, let me address it now. This is not important, other than if you want to dispute my estimate of 1988, which is fine. But I'm not going to, my rule would just be round to the nearest whole number and convert it to a year. But the idea is when t is equal to 7 and t is equal to 8, this represents the year 1997. Sorry, 1987. This This represents the year 1988. And if you had a value of t for the estimate, either the equation or the graph, and you decided it was 7.58, 7.58 would be right about there. And that's like maybe August or September in the year 1987. You haven't quite reached New Year's of 1988. So in August or September of 1987, you don't round up to 1988. You just say we're still in 1987. So you tend to always round down. Like where are we at now? We're in October of 2020. If we round to the nearest year, the nearest New Year's, we would round up to 2021. But we don't do that. We just say we're in 2020 until January 31st. We're still in 2020, and we only talk about being in 2021 when we hit New Year's of that year. I was not intending you to think about that and worry about that and stress about that, so I'm not going to worry about that. I'm going to treat it as a basic, you just round to the nearest year. So you're going to round this to 8, and it's going to be 1988. So just round to the nearest year, don't stress about that kind of thing, about what we would actually use in real life. Okay, so I just want to address that, but because some people really think it through and think, oh, that's actually in the middle of 1987, and we would still say 1987. Nah, just round to the nearest year. It's fine. Okay, more to do, but pausing. Okay, oh, I forgot what was that, A, B, C, D, E? That's not it, just follow along. Okay, next we're going to the same model. We're still working on the same model. We're going to calculate the v-intercept. Or I should say use the equation. Oh, no, I'll just say using the equation. It's still using the equation. Calculate the v-intercept using the equation of your model. We're going to use equation and explain what this point represents. The next question, part E, will be calculate the t-intercept using the equation of the model and explain what this point represents. And so this is something we did in homework 12, and I would have you estimate the intercept by estimating the coordinates of the point where it crosses the v-axis, and then as a separate problem I had you explain what does that point represent as far as the value and the year. Here it's combined into one question, but we can think of it like two questions in one. We're going to get the coordinates of this v-intercept, not off the graph, off the equation, and then we'll explain what it means as far as the value goes. Okay, but we're not doing it off the graph. We are using the equation of the model, so we're using this. But before we start, anytime I do intercepts, anytime, I'm going to recommend that we first figure out where that zero goes, because the key thing, sometimes people are confused about it, and I do get a lot more questions about anything else. It's the intercepts that people don't know how to start it. And I'm going to tell you how to start it right now. Any intercept question, figure out where the zero goes. Both intercepts have a 0 as one of the coordinates, and you have to find the other. And let me keep it straight. This is going to be t, and that's going to be v. Like x, like y, but I need to know that it's going to be the v-intercept is where my graph would cross the v-axis. If I didn't bother to do this graph, and I wanted to make sure or think about where that 0 is, I would draw a little mini graph. And I would know that t is like x, v is like y, and I would draw a very crude line. And then just think about that point right there, which would be the v-intercept, and which coordinate is 0 when it's on the vertical axis. It's like a y-intercept. It's 0 comma something. 0 is t, and the v is unknown. That's how you start an intercept problem. Figuring out where that 0 goes, which coordinate is 0, and then use it. Either look it up here, or in this case, plug it into our model. So our t is 0, our v could be anything. We're going to find out what it is. Using the equation of our model, not the graph. All right, I'm going to plug in right here. T is equal to 0. Once you remember to just figure out what the 0 is, it's a matter of just plugging in that 0. And then finding the v that corresponds, which means v right here by itself, and I get my answers to whatever I get when I simplify that. 0 times anything is 0, plus 7.64 is going to be 7.64. That's it, 7.64. Now you can note that that is like a y-intercept. So this is of the form y is equal to mx plus b. That's your b right there, and that's going to be the y-coordinate of your y-intercept. In this case, we're looking for the equivalent of a y-intercept, so that's why it's just that constant term for this one. The other one's going to be more difficult, and I can't tell by glancing on. I mean, I can estimate it, but it won't be evident from the equation we'll have to solve, so that's not going to be as obvious. But just remember to plug in the 0 first. All right, we're not done with this problem because that's my intercept. And now I need to explain what that point represents. The t is 0. What does t0 mean? T is the number of years, go back to the definition, t is the number of years since 1980. That's 0 years since 1980. That is 1980. So your information is always based on a year, and the other thing is a value. V is the value in thousands of dollars, and so since the B is 7.64, that represents $7.64 thousand. And so your information interpreting any ordered pair for this particular problem, this context, you have the year and the value. The T represents the year since 1980, the value in thousands of dollars. So any explanation about any point, intercepts or otherwise, will include a reference to whatever year it is, and a reference to whatever value the car had in that year. So your kind of template for explaining a point could be in the year blank, the value is blank. That's what I've set up here. I'm going to use the same template for my t-intercept as well. All right, anyway, let's go back to what I just talked about. T is 0, that's the year 1980. The value is V, that's 7.64, but that represents thousands of dollars, so make sure you type down, it's not $7.64. $7.64 thousand. And you can round that if you want, but they didn't really specify, so I'll just leave it as is. And that's your explanation. In the year 1980, the value is $7.64 thousand. That's using the equation. We did do it in homework 12 off the graph. If I did it off the graph, ooh, that's why I said my thing is way off. Yeah, my graph is not good. I would have said $8.5 thousand. Still 1980, but my estimate would have been off because my graph is hand-drawn and not accurate. Anyway, I think my 2.4 is too high, that's why. But anyway, we're not relying on that. We're relying on the equation, which gives us more accurate answers anyway. Part E. Use your model to estimate, use the equation of your model. Use the equation to estimate the t-intercept and explain what this point represents. Ooh, I need space for this. I'm thinking about what I can erase. Kind of wanted to leave this up because I wanted you to see that I'm going to be doing roughly the same thing, but nah, I'll erase it. You have it in your notes. I'm going to tell you right now, I'm going to do it in this very similar way. Organize it in a very similar way. But probably a little bit faster this time. Okay, it's a problem where we have to estimate or find the coordinates of an intercept. It's an intercept problem. And right away, I'm going to do the work up here. For an intercept problem, I just mentioned for probably a third time now, the best way to start it is to figure out where the 0 goes, the ordered pair. Make sure you know which one is which, where the t is and where the v is. T is like x, v is like y. If I didn't have that picture there, I would think about which one's a t-intercept, which one is 0 on a t-intercept, so I draw a little mini graph here. Again, I'm pretending I don't have that, I didn't take the time. Remember, they never told us to graph it, so in theory, we'd be doing this whole thing without a visualization, so we could be trying to work this out with just numbers and equations. Anyway, I would definitely want to visualize or draw a little mini graph at least. A model going down like that. Note that my t-intercept would be along that horizontal axis. Think about which coordinate is 0. That's going to be blank, comma, 0. My t could be anything, but my v is going to be 0. And that's what I'm going to fill in. 0 for v, blank for t. And now I know what I need to do. I need to take my equation, because it says to use the equation. And I need to plug in the value that I know, and I know the v is 0. So I'm going to plug in 0 for v right there. I'm going to find the t that corresponds to it. And this time it's not as easy as the last one because I have to now solve for t. So I do the solving of an equation. I'm going to subtract 7.64 from both sides. There's other ways you can do this, but we should get the same answer as long as we do it correctly. 0 minus 7.64. Don't lose that negative. Don't worry about it, the fact it's a negative. I'm going to be dividing by a negative 0.48. The negatives will cancel, and I'll get a positive t. All right, I don't know what that is. I got to get my calculator. 7.64 divided by 0.48. 15.9? 9.2 if you round it, but yeah, that's good enough. Okay. 15.9, 15.92, they didn't really specify where to round it, so either one works. I'll use 15.9. Okay, if we did it off the graph, I don't know, I would have said 16, but yeah, close enough. Okay, anyway, more accurate answer from the equation, and now let's explain. Don't forget we gotta explain. My explanation is going to be in the year blank, the value is blank. Again, that's my template for explaining any point, because any point on this problem, on that graph, gives you a year, or gives you information related to a year and related to the value. Alright, what year is this? We're looking at this. T is the number of years since 1980, so I'm going to use this T to find the year. Now that I think about it, 15.9, we don't do decimal years, so that's fine leaving it like that, but for me giving a year, I definitely need to make sure I convert that to a whole number of 16. Add it back to the reference year 1980. Let me do it out here. So the t is equal to 15.9, so I'm going to treat that as t is equal to 16. Add back the reference year. That's 1996. In the year 1996. What was the value? Value is v. The value is $0. You can put the car was worthless. That's fine. That tells me the value is 0. But I'll just go with saying the value is equal to $0. All right. And my answer there says the car will be worthless in 1996. That's my explanation. Close enough. That's the same thing. Anyway, that's it. You can see the value declines. Like whenever you have a car and you run into the ground, eventually you can barely sell it on Craigslist. And the model says it's worth $0, even if you think you can get a couple $100 off Craigslist. The model says it's worth $0. All right, we're going to do another example more quickly this time, but starting from scratch with a new data set and a new context. Okay, starting fresh with a completely new problem. The population of Springfield increases linearly from 54.3 thousand in 1992 to 96.7 thousand in 2003. Let PV be the population in thousands. And T the years since 1990 is the reference year this time? Okay. So same sort of question, I condensed it a little bit, but same idea. They didn't ask a question yet. Our first question is, find the equation of the linear model. That describes the data. We're going to have that same issue of where we have to round our slope and our y-intercept, so we're going to round figures to 2 decimal places as before. Again, I'm shortening the way I write things for brevity, but sorry, round to 2 places, round your figure to 2 decimal places. Okay, we're not going to graph it, where they didn't ask us to graph it, and I'm going to pretend like we're not going to graph it. And we can just work it out without referencing a graph and understanding and having a visual idea of what it means. It'd be good to, like, I'm not lying, but let's see if we can work it out without doing that. All right, so you need to find the equation of a linear model, and to find the equation of a line, you need all those things you would have needed in homework 15, 16, homework 15 rather. You need either 2 points or you need the slope and a point. But here, just like last time, they're giving us 2 points, two populations in 2 different years means they're giving us essentially 2 points in this linear model. So, as before, you shouldn't start trying to stick numbers in here, or wait, no, we're doing slope first anyway. Don't write this down, I'm just kind of going over what we will be doing. You're going to be doing slope first, then using slope and one of the points in point slope form. I would not start trying to grab values and plugging in straight there. I highly disagree with that strategy. I feel like you're really going to be prone to errors. My recommendation is always write your ordered pairs. It also keep straight which is T and which is P, and you can organize it and keep it a lot more organized in your mind if you list out ordered pairs first. Now, I said we're not going to graph it, or at least not yet, but it will help me to actually maybe draw a little mini graph. This is not going to be an accurate one by any stretch, but just to kind of keep track of where the T and the P would be. T is your independent variable. Years for population growth or value decline or anything like that. Your years is an independent variable, so T is going to be there, and P is going to be there if you were to graph it, which we're not. But so that helps me know that I want T first and P second. T first and P second. Okay, now let me grab these 2 points from the paragraph there. The population was 54.3 thousand. That's P. In the year 1992, which is a T value of 2. And then the other point is the value was $96.7 thousand. In the year 2003, which is a T value of 13, not 3. Be careful. Okay, so you can't just grab the first number and make it the first coordinate and the second number and make it the second coordinate, because it depends which one is the dependent and independent variable. Okay, and now we're ready to go. Now I'm going to do what I do for 2 points to find the equation of a line. First doing slope, 96.7 minus 54.3 over 13 minus 2. Common mistakes here are having the coordinates in the wrong order, also misinterpreting 2003 as t is equal to 3 and not t is equal to 13. All the things that I mentioned just now. 96.7 minus 54.3. I got 42.4 for the top only. 13 minus 2 is 11. So I'm going to divide this by 11. Okay, and I got something like that, but I'm going to round it to 2 decimal places, so I'm going to round it to 3.85. It's positive. That indicates that the population is growing, and without even, if we saw the graph we could see that, but if we don't have a graph available, you can see it's a smaller population in an earlier year, and then a couple of years later, specifically 11 years later, the population has grown, so it's definitely going to be an increasing model with positive slope, positive 3.85 specifically. All right, I'm ready for point slope form. Either point works, but they might give you slightly different answers, but both are valid. I'm going to use the first point. Okay, and then I'm going to rewrite it in y is equal to mx plus b form. I'm going to distribute the 3.85. 3.85 times x minus whatever I get when I do 3.85 times 2. $7.7. Left side is still as is to get the y. Oops, I forgot my x. And then I'm going to add 54.3. And y is equal to 3.85x plus or minus something, which I don't know yet. I'm going to do 54.3 minus 7.7. Same thing as what I have up there. 46.6? Yeah. Remember that you're giving a linear model for p and t are your variables, so you need an equation with p and t, so we're not technically done. I need to write this as p in place of y and t in place of x. And that's going to be to my benefit anyway. First of all, you get full credit for this. You don't if you leave it as y and x. You get -1. But also it makes it easier for us to know where to plug in population and where to plug in the years since 1990. So the choices of letters helps us, variables helps us to keep them straight when we do the follow-up questions. But anyway, that's part A. That's number 1. Use the model, sorry, use the equation of the model. Let's go to use the equation. To predict the year in which the population will reach 130,000. There's no graph to help me visualize it, but if I know what these things are, I can know what I'm doing. I need a year, which will be related to the t that I get. I need to be plugging in population, and they give us population. So I'm going to use the equation now, the equation of our model. Just plug in the information that it gives us. And the information that it gives us is p is equal to however many thousands the population is. So you're not going to put 130,000 here, you're going to put 130. Again, you got to be consistent with the way the population is given here. That's 54.3 thousand, even though they only write 54.3 as their coordinate. The other one is 96.7 thousand, even though they only use 96.7 as a p coordinate, or as a p value. And so here we need to be consistent with that, not 130 with 3 zeros, just 130. I'm looking for the year, so I'm going to be solving for t. I'm going to do it rather quickly. I'm going to subtract 46.6. $83.4. I'm going to divide by 3.85. 21.66. Okay, let me clarify what I need. That's solving for the equation for t when I plug in 130, but I need a year as my answer. What year is that? I'm going to round to the nearest whole number, which rounds up to 22, and I will find what year that is. That's t is 22, means 22 years since 1990. Make sure you know it's a different reference year for this problem than the last one, so now our reference year is 1990, right? Wasn't it 1990? Yep. Okay. So that is going to be 2012. That's it. Very similar to what we did before. Okay. I guess I'm done with all this. Use the equation to estimate the p-intercept. And explain what this point represents. So I'm only doing a couple of each of the types of problems. I did it very thoroughly in the last example where I did every type of thing you're going to see. Here I'm just going to skip and do a few of them, explain what this point represents. So I'm only doing one intercept, the p-intercept. Okay, well, so we'll explain what the point represents later. For now, we need to figure out the p-intercept, and that's going to be a point. Any intercept is an ordered pair, and the way you start, once again, finding the coordinates for an intercept is to figure out where the 0 is going to go. So one of the coordinates is going to be 0. Which one is t and which one is p again? If you can't remember, a little mini graph helps you to remember it, keep it straight. If you're going to graph the population of Springfield over the years, you can see years along here. That's t. Years are going to be your independent variable like x. Your population is going to go up going that way. So p is your dependent variable, depends on the year, and therefore that's going to be like y. T like x, p like y. And the model, I didn't draw it, I'm not going to draw it accurately, but the model is going to be upward sloping because again it has positive slope and it's increasing population. The main thing is I'm only doing this so I can visualize a point on the p axis and remember what coordinate is 0 for that. It's like a y-intercept, and the y-intercept is 0 comma whatever. So my t is 0, it's along here. Right there is t is 0, t is 1, t is 2. Nope, it stays on t0, so it stays right there. P could be anything, it could be anywhere there. Again, this is not an accurate depiction of it, but it gives you a visual idea that your t coordinate is 0 and your p coordinate is what you have to find. All right, my equation, I erased it, but I still have it right here. And now I use the equation and plug in the one coordinate that I do know. And I know that a t coordinate of 0 is what's happening with this p-intercept. Plug in 0 right there for t. And solve for p. And since p is already by itself, I'm just going to work this out. N times 0, 46.6. I get p is equal to 46.6. That's my p-intercept using the equation. Explanation. What have we got? T is the years since. P is population. My template for an explanation is in the year blank, the population was blank. That's my explanation of a point, explaining both coordinates. Which one is which? The t gives me the year since 1980. Sorry, no, that's not right. My reference here is 1990 now. T is the number of years since 1990. T is 0 is going to be the actual year 1990. The population is P in thousands. Is that right? Thousands? Make sure you read, because sometimes it's millions or it could be billions, but here's thousands again. So my population was 46.6 thousand. According to the model, that's what the population would have been in the year 1990 based on the data that we have. Okay. This one's a little bit new. Use the equation to estimate the change in population from 2001 to 2006. I had you do a couple of these for homework 12. And you have to remember your change in quantity formula from homework 2. Was it 2? No, it was homework 1, I think. It was way back. But I use this notation, which I've used since. Change in population, so P's population. We're looking for the change in population. That's a notation for it. You don't have to really use that, but you do have to know what you're doing to do it. And you're subtracting the population in those 2 years in a particular order of final population minus initial population. And let me be even clearer about it. The final population, here's your starting point in your initial year and your final year. So we got to calculate the 2006 population, we have to compute the 2001 population, and then we subtract the final population minus the initial over that period. So it's 2006 population minus 2001 population. Again, that's your final value, that's your initial value. We need those two values, and we don't have them right now. And on the homework, those values were from previous problems. I didn't make you do new ones, you could just grab it from previous problems. If you look back on what we did for this Springfield problem, did we do the population 2001 or 2006? We did not, so we gotta do these fresh. I'm gonna erase here. This takes a little bit of work. But just make sure you don't get overwhelmed by that work, because they're just baby steps. There's a couple of simple problems in sequence and then putting them together. So first sort out what you need. You need the population in those 2 years. That's essentially two separate problems. You don't need to organize it as thoroughly as I'm going to do, but I'm going to calculate the population in 2001. So this is essentially a new problem. Use your equation to estimate the population in 2001. Oh, should I erase my equation? You have it in your notes. I have it right here somewhere. And what I want to do is find the population in the year 2001. I need a t-value. My reference year is 1990, so 2001 is t is equal to 11. I'm going to plug in 11 for t. I got 88.95. Yeah. That's your population in 2001. You don't need to be as wordy with this as I am. This is more for your notes. I'm also going to need the population in 2006. Okay, what t-value am I plugging in for that? 2006, my reference year is 1990, so that's 16 years since 1990. I'm going to plug in 16. $108.2 thousand. In the year 2006. Okay, so now I know the population, based on our model's estimate, the population in 2001 is 88.95 thousand. In 2006, it's 108.2 thousand. I want to know the change in population from there to there. So I'm going to go back to that. Change in P is equal to final minus initial. I was more specific about it here, just to keep track of the fact that the final year in this period of time is 2006. So 108.2 goes first, minus 88.95 goes second. And the order matters, because you can have a situation where you subtract a smaller number minus a bigger number and get a negative change, which represents a decrease. But if you have a increasing population, it's going to be bigger minus smaller, and you get a positive change. So the sign and the order does matter for your change in. Again, we did this in the first exam on homework 1. It was crucial that you understand and remember you're doing final minus initial. 19.25. Didn't really say a word around it, so you can run it to 19.3 if you want, or you can leave it as 19.25 thousand. Anyway, that's a change in. One more thing and we're done. Okay, problem says sketch the graph of your linear model, or the linear model. Okay, so now they want us to graph it. I said we could do the whole thing and all the computations without the graph, and I wanted to show you that you can. But occasionally it was helpful for me to actually draw a little mini graph so I can make sure I know which one is a T and which one is a P. But here we're going to do a full graph, so no big deal. I had my 2 points, which I erased, but let me put them back. It was T, then P. I did this earlier. You have it in your notes, but I erased it, so I got to go back and make sure I can grab those points. Where were they? It was 254.3 and 1396.7. Okay, and I didn't really scale it, but I'll go by fives again. 5, 10, 15. That's my T. T is your independent, the years. Value, I'm going to go to by 20,000 or 20, 40. They represent 20,000, but your actual values are 20, 40, 60, 80, 100. Oh, I should go higher actually. Oh, I should go way higher. I just realized. I want to use this graph to illustrate a couple of things, and I need to go a certain height. I'll go to 140, that should be enough. Okay, and to sketch this model, based on just, again, all that was given in the original problem was just the population in 1992, the population in 2003. We picked out and made 2 ordered pairs of it and used it to find our equation, but we can also use these 2 ordered pairs to plot 2 points and then draw a line through them. 2, 54.3. I'd say about there. 13, 96.7. And this graph is really this is really crude. Okay, we'll draw a line through it. And that's the model. The equation of that line is V is equal to 3.85T plus 46.6. You don't need to label it, but I want to make sure you understand. This point was the 2,54.3. I shouldn't do that in red. I want to emphasize things as we go. 254.3 I plotted there. 13, 96.7 is there. And the equation of the line that we found via those 2 points is that's the line passing through those 2 points. Okay, and we're done, but I'm not done. Let me go back and look at some of those other problems that we did, because a lot of times I want you to compare what you get off the equation and what you get off the graph. They'll make you do both. I'm not going to waste time doing it, but in theory I could have you estimate the year in which the population was 130,000. So I'm going back to one of the problems we did earlier, 130,000. Right there. Oh, this a hand-drawn graph again, and I got to extend that line, but basically we will go to 130 along the P, which I forgot to label. Estimate the year. All this crap's in my way, but what am I saying, 16 or 17? What was the actual answer? Holy smokes, it was 22. My graph is way off. Anyway, you would get, if you had an accurate graph, it would be 22-ish, because that's what we estimated. And then what was the other thing we did? We found the p-intercept, which I erased. Okay, p-intercept was here. I would say that's below 50, so 49, 48, what did we have? It was 46.6, okay. So that's the idea. 130,000 should have came out to about 22. It's off because this is a very crude graph. P-intercept we did, which we found to be 46.6, which is through the equation, which is more accurate. That's about right, but my graph is way off over there. Again, I was doing it half-assed. Anyway, make sure you understand the relationship between things you can get off the graph and things you get via the equation. They should be very similar, and they'll be more similar if your graph is nicer and more accurate and more thorough. Mine was not. But make sure you understand that relationship between the two, and pay attention to the problem where it says use the equation of your model, means you're plugging things in, or using the graph of your model, in which case you're doing that. And all graphs will be provided for you, all lines will be provided for you, because again, I can't rely on people having graph paper or being able to print out things. So I will have to do it for you, and you can keep it on your screen and then just do this kind of thing. And it'll be more accurate, I promise you. I'll make it super accurate on the homework. That's it for whatever lesson this was, 18. Wait, we're not done. I feel really bad about my hand-drawn graph giving us such bad predictions. Real quick, let me just do a more accurate one, making sure we understand. For the last problem, the Springfield problem, which we did purely based on equations. My points were, let me do it in a nicer graph so we can see, just so you understand where things came from. 2, 54.3, real quick, and 13, 96.7. A much better graph, more accurate. I drew the grid line so I can be clear about where things are. 2, 54.3. I want to say it's right there. 13, right there, 96.7. Right there. Let me grab my... Look at it a little bit further, because I'm going to do 130. Okay. Let's see real quick. We did an intercept. I would have said that 0,49. Our actual was 0,46. It's still not accurate because it's still hand drawn, but a little more accurate than last time. 130 we did. I would have said 24. Our actual answer was 22. But again, more accurate. Again, still hand-drawn graph, still not accurate. But that's the idea when we do 130. We're estimating the year in which the population was 130. This is our crude estimate, but the equation got a more accurate estimate of 22, which was 2012. We estimated the p-intercept. Looks like it's 49, but our equation gave us more accurate y-intercept or p-intercept of 46.6, and that was the population in the year 1990. Okay, but anyway, it's just analogous to what we were doing via the equation, but the emphasis in this particular homework is using equations to do things that we used to do crudely via a hand-drawn graph.